last time we defined the extrinsic curvature. It tells you how a hypersurface sigma is embedded into a spacetime M. So let me write our notation again. So our hypersurface sigma has coordinates yi and reduced metric hij. Our big spacetime M has coordinates x alpha and metric g alpha beta. And so last time we introduced the extrinsic curvature and talked about how derivatives within the hypersurface are related to the ordinary spacetime derivative. And now I want to give a couple more equations and then go on to some related things. So the equations that I want to give, I'm not going to derive, but these are equations that relate the curvature of the curvatures as defined in this manifold, the submanifold sigma, to the curvatures as defined in the spacetime manifold M. So the derivations are basically all the same tricks that we used last time to derive the relationship between extrinsic curvatures and derivatives, intrinsic and extrinsic derivatives. But these are more annoying, so I don't want to do this on the board. So these are called Gauss-Cadazzi. And I'll just write them to give the flavor. Okay, so Gauss-Cadazzi tells you how to relate the curvature, the spacetime curvature R A, B, C, D of G to R A, B, C, D of H plus extrinsic curvatures. Epsilon naught is n squared plus or minus 1 times k AD, k BC minus k ABC, k BD. So what's going on here? We're going to use these later, so let's understand what's showing up here. So R bracket G, this means the Riemann curvature that's built from the metric, from the spacetime metric G. But I have A, B, C, D indices here. And the ordinary Riemann would have alpha, beta, gamma, delta indices. So what I mean by this is the pullback of that. So it's P alpha A, P beta B, B gamma C, B delta D of R alpha beta gamma delta. So if you take the space-time Riemann tensor and you pull it back to the hypersurface, and this equation is telling you how to compare that space-time curvature to the intrinsic curvature on the hypersurface. So this equation kind of makes sense. It just says that the space-time curvature has two incarnations on the hypersurface. There's the intrinsic curvature of the hypersurface and the extrinsic curvature of the hypersurface, and these are both related to the total curvature. So the second one is for the single contraction of this formula. So mu dot R mu ABC of G is equal to dC K AB minus dB K AC. So this tells you that, so here all the indices were along the hypersurface. Now 3 of the indices are along the hypersurface and 1 is in the normal direction. This equation says that that object can still be expressed in terms of data on the hypersurface. In this case, intrinsic derivatives of the extrinsic curvature. The other components of Riemann, for example, n mu and nu, are mu nu AB, sorry, A, that's 0, and nu R, nu A, nu B are not determined by Hij and Kij on the hypersurface sigma. That makes sense. So if you think about the Riemann tensor as defined by moving vectors around a path, then if that path that you're talking about stays on the hypersurface, then it sounds reasonable that your definition of curvature should be expressible in terms of tensors defined on the hypersurface. But if you take one of those paths and do parallel transport around the path on a loop that goes off the hypersurface and then comes back on, that's really not data about the hypersurface. It's data about the space-time. And if you had some whole family of hypersurfaces like this, then if you knew H and K on all of these hypersurfaces, you could put that information back together and reconstruct the entire manifold, including the Riemann. But we're talking here about the case where you say you just know H and K on one of these hypersurfaces, then you can't determine, you can only determine the all tangent and mostly tangent pieces of the curvature. You can contract indices on this. I'm going to write the result so that we have it. So if you contract some indices, you get -2 epsilon naught G alpha beta, and alpha and beta equals R of H plus epsilon naught KAB minus K squared, and G alpha beta and beta equals D B KBA minus DA K. So this thing is the Einstein tensor, full manifold. I've just contracted some indices on Riemann to get the Einstein tensor. You can contract again to get so R of G is equal to R of H plus epsilon naught K squared minus K of B, K of B plus 2 epsilon naught grad alpha and off grad alpha minus n alpha K.
I'm a bit confused about the first relation there because you already said that nu are nu a, nu b, not be completely determined by H, I, J, and Kij on the sigma. But if you look at the first relation there, which is saying about G alpha beta and N alpha and M beta, it seems like you completely determined some information on Riemann tensor on the manifold by just using some manifolds cover chain of the method.
I guess the point is that this thing is not determined, but its trace is determined.
Oh,
And here we're told to use its trace.
yes. So if you have trace of that, then could you express in terms of H and K
let's see, I guess so, because the trace of that is the Ricci tensor. And using these two equations together, we can get the Ricci tensor. Yeah. Other questions? You're questioning how we can contract things here and get to there. I actually don't remember the steps, but they're in the book. They're in any of the books, and it is possible to go from there to here. Okay. Now I'm going to discuss the initial value problem. Take one. So we're going to come back to the initial value problem later when we discuss the Hamiltonian. But I want to describe for you what the initial value problem is and see how far we can get. So first of all, what's an initial value problem? It's easier to give you an example than to tell you. So it just means that when you solve physics problems, you often like to specify initial conditions and then ask how they evolve in time. So for example, if we have a free scalar, we write box 5, m squared 5. We specify the initial data at t equals 0. It's a second order equation, so the initial data is the value of the field, 5, 0, x vector, and phi dot of 0, x vector. These are two free functions. You can make them whatever you like. And if I give you these two free functions, then you get a unique solution of the differential equation on what I'll call d of sigma. So let me say initial data at t equals 0 on some domain sigma. D of sigma is the, so if this is sigma, where you gave me the initial data, then d of sigma is the stuff to the future. It's called the domain of dependence. And the technical definition, it's just what you think it is. It's the part of the future. The technical definition is that every point, if you take a point in d of sigma, then every path-directed causal curve has to intersect the surface sigma. So that's the domain of dependence. And you can prove mathematically that this is true, that this is a well-posed initial value problem. So this particular type of partial differential equation is called a hyperbolic PDE, and hyperbolic PDEs have good initial value problems in this sense. You give me the data on some domain, and I can uniquely hand you, if I know how to solve PDEs, at least in principle, it uniquely specifies the data in the future. Okay, so what is an analog of this? The initial value formulation of general relativity is supposed to give a version of this for gravity. Now for GR, it's going to be much more complicated. And I want to quickly give the example of E and M, because GR is a lot more like E and M than it's like a scalar field. Although there are differences there too, so let me give example 2. Free Maxwell. So the dynamical variable here is the vector potential, A. And the dynamical equation is Maxwell's equation, grad mu f nu is equal to 0. Now, at first sight, this is 4 equations for 4 unknowns. 4 equations for 4 unknown functions, so you might think that you're in a good spot. But actually, this is not a well-posed differential equation for the vector potential. That is, if you hand me a mu at time 0 and a mu dot at time 0, that's certainly not going to give me a unique solution of the vector potential at later times. The solutions are not unique given a mu dot at time 0. So we can't solve that equation in this sense. Now, physically, there's a very good reason for this, and it probably doesn't bother you because we know exactly why. It's because of gauge invariance. You know, the vector potential isn't supposed to be fixed by the initial conditions, because you could evolve for a bit and then do a gauge transformation, and that's physically equivalent. So you're not supposed to have a well-defined initial value problem for the vector potential. Of course, you'd still like you want some kind of well-defined initial value problem. You still want the physics at time 0 to determine the future. So the right way to do that in E&M is to instead formulate this in terms of stuff that's gauge invariant. So that is, you specify the electric and magnetic fields at time 0, and ask, are E and B uniquely fixed at later times? And that does work. So in E&M, the initial data, the correct way to think about the initial value problem is that the initial data consists of f mu nu at time 0, and dt of f mu nu at time 0. That is the E and B fields. And these are supposed to give the fields uniquely at late times, and they do. But there's a subtlety here, which is you can't just hand me any old E and B field. The E and B fields that you give me at time 0 must obey the Gauss constraint. Which, in terms of the Maxwell equation, is just the T component of the Maxwell equation. So that's d mu f mu t is equal to 0. So this is divergence of E equals divergence of B equals 0 in ordinary vector notation. So the T component of the Maxwell equation is not a dynamical equation. It doesn't tell you how fields evolve. It tells you what fields you're allowed to start with. So this is called the constraint, and you can tell it's a constraint because there's no second time derivatives in this component of the Maxwell equation. You can convince yourself of that by if there's a t here, then there can't be a t there because f mu is antisymmetric. Okay, so if you have an equation with no second time derivatives, then this is not an evolution equation. It's an equation on the actual data at time 0. You're not allowed to slap down any old B field. So the initial data is the E and B fields subject to this constraint, and then the other equations, grad mu f mu I, where the I equals the space directions, gives you unique dynamics in the sense that the E and B fields at later times will be uniquely determined, so you again have a well-posed initial value problem. Okay, now GR, yeah.
The fact that this is a constraint, does that have to do with the fact that the right-hand side is 0, or is it only because there's no second derivative?
It's only because there's no second derivatives. This would, if we had some charges present, so if we had a current here, this would still be a constraint equation. And what it would say is that del dot E is equal to the charge density usual Gauss. It's still a constraint equation because it tells you what kind of fields you're allowed to have at time 0. Yeah.
So in what sense do we need dt of f mu nu if we use the equation of motion? Can we just write that in terms of the partials over the spatial partials? So if you give me f mu nu at t equals 0, you can just write, you can just take the derivative with respect to the spatial component and find out dt. So why you need that?
You're saying this is extra?
Yeah.
So I don't think it's extra. Say again how are you going to get it?
The equation d mu of f mu nu. So
Um,
Yeah, you're right. Question for F is just first order, so.
oh.
or maybe it's just dt of some components that you can get, not dt of any component. For instance, dt of fij, I don't think you can get it from the equation. Okay.
Some of these just sort of automatically,
Yeah.
some components of this will automatically vanish by the Gauss constraints,
Yeah.
and the other components I think are actual initial data.
Good.
Yeah. So again, you get unique fields for domain of dependence, you get a sigma. Okay, is this clear, the distinction between constraints and dynamics? Now we're going to do GR.
Does it need to be no dt squared? Because surely that's stronger, there's no dt.
Sorry?
I mean, you say there's no dt squared in that equation, but isn't it stronger? There's no dt at all.
I meant on A. I mean, in the sense
Oh,
that
okay.
as an equation on A.
Oh, so we're going back to the a.
Yeah, yeah. Okay, so in GR the goal is similar. We would like to have some initial conditions that specify some space-time. So we want to fix space, we want to give you a space. In some sense, we want to give you a space and find the space-time. And this is tricky because now we don't just have some manifold where we're trying to find the fields. We actually have to find the manifold itself. And so it's not obvious what initial data should mean. Roughly speaking, we would like to specify some slice. Okay, so now we go to GR. Roughly speaking, we want to specify some slice sigma and tell you the data on that slice and then evolve in time. Given what we've discussed about hypersurfaces, I think that what I'm about to say is a plausible guess for what the initial data is, and I'll just state it. We can mostly derive it. So the initial data is Hij and Kij. That is a 3-dimensional, so say we're doing 4-dimensional gravity, then the initial data is a 3-dimensional metric and a 3-dimensional extrinsic curvature. Remember that extrinsic curvature, I guess I erased the definition, but remember that this was the Lie derivative of h along the normal direction. So when you see extrinsic curvature in this context, think h dot. Okay, extrinsic curvature. So h is like the field, and extrinsic curvature is like its time derivative. I put it in quotes because I don't quite mean that literally, although depending on our slicing, it can actually literally, if we choose a slicing, if we have a static space-time and we slice with a t coordinate, it's literally. Now, as in the Maxwell case, you can't just throw me any combination of metric and curvature. It has to obey the constraint equations. So the constraint equations are g mu nu and nu is equal to 8 pi t mu nu and nu. So what is going on here? Is just like in the Maxwell case. The constraint equations are the equations that have no second time derivatives. And it's not, okay, you gotta think through where all the Christoffels are and everything, but it's true that the equations that I've written here have no second time derivatives. This is just the Einstein, it's the pieces of the, there were, how many Einstein equations? 10 Einstein equations. Is that right? There are 10 Einstein equations, and 4 of them, these 4, have no second order time derivatives. You could basically, these are the, if you want a more coordinated way to think about it, these are the GTT and GTI. I'm going to put that in quotes because that's specializing to a particular coordinate system, and we like to keep things coordinate varying. But in your usual thinking about things, these are the time and the time-space components of the Einstein equations, which are precisely the ones that have no double time derivatives. Now, to convince you that these are really constraints, I should show that, well, to convince us, for these to actually be constraint equations, they have to be equations that can be written in terms of h and k. The other components of the Einstein equations cannot be written in terms of h and k, because they'll also involve things like k dot, which is double time derivative. But these equations, it should be possible to write in terms of h and k. And that is possible because of the Gauss-Codazzi relations that I wrote on the board 15 minutes ago. So remember, we said that certain components of the curvature could indeed be written in terms of the data on the hypersurface. Well, these are precisely those components of the curvature. So the constraint equations rewritten in that language are as follows. So I'm just plugging in the Gauss-Codazzi relation. R of h plus k squared minus KAB equals 16 pi t alpha beta and alpha and beta which you should think of as being 16 pi times the energy density in as measured in the frame that we're working. Is the normal, these are like the time components of the stress tensor, which is basically which you could think of as the energy density. If this were, say, a perfect fluid, then this would be the same rho that we talked about in the context of perfect fluids. More generally, it's just a definition of T dot n dot n. That was the, this was the norm. So we have 4 equations here. That was the normal part, that was dotted into the normal vector, that equation. And now I'm going to give the tangential part of that equation. So it says dB, k, A minus EAK equals 8 pi T alpha beta P alpha A and beta, which you could call 8 pi JA. Same kind of thing here. I'm just defining these pieces of the stress tensor to be some momentum current. Momentum tensor. Then the time evolution corresponds to the other components of the Einstein equation. So the space. So in 4D there are 6, in 4D there are 4 constraint equations on the initial data, and then 6 evolution equations that tell you how that initial data evolves with time. Einstein equations equal 4 constraints plus 6 dynamical. These 4 constraints, as we'll see, you could think of as as being just like the Gauss law that we had in E&M. So in E&M, del dot, the divergence of E is equal to 0, or the charge density. That was the constraint equation in Gauss's law. These 4 constraints are basically Gauss's law for energy and momentum, or Gauss's law for form momentum. And they're going to tell you that if you have some data on a hypersurface, then the fields very far away, the fields, the asymptotic values of the fields are related to how much energy there is and how much momentum there is on that slice, just like the electric field in Maxwell. And at least for the vacuum Einstein equations, where the right-hand sides are set to 0, you can prove that this is a well-posed initial value problem. In the sense that if you give me H and K are being these constraints, then you can solve the evolution equations to find a unique space-time on the domain of dependence. T of sigma. Now, what you mean by unique, you have to be careful. In Maxwell, unique meant that the E and B fields are determined uniquely. Here, we mean that the curvatures are determined in space-time. You don't want to specify the metric uniquely because it's not different there. Do this, change this. Okay. Questions?
So all curvature tensors? So the curvature, what you're saying the curvature tensors?
Yeah, the full space-time curvature tensors on D of sigma are unique for this initial value problem. That is, initial data, then evolved, gives you a unique answer on D of sigma.
I have a question. Could we start with a time-like hypersurface and kind of evolve in a space direction to find a solution?
Generally, no. Generally, no. So that doesn't work. So it's actually, it was the type of the type of PDE, as we saw in the free scalar versus Maxwell case. The details of the PDE are important here as to whether they give you a unique solution. And the type of PDE that you get evolving forward in time is a different type of PDE that you would get if you tried to specify data involved sideways. And you can find examples. In fact, there are important examples where you definitely cannot evolve sideways in the Einstein equations. Yeah.
Why is the non-appearance of a second time derivative good enough to say that something is non-dynamical? Why is it in that like the first derivative?
Well, it's basically because we think of the initial data as the field and its first derivative. So any equation that can be written entirely in terms of the field and its first derivative is called a constraint. Because it depends only on the data on a given hypersurface. You don't have to go off the hypersurface to ask whether this equation is satisfied or not. So those are the constraint equations. The dynamic equations are comparing the data onto nearby slices. So it's a different kind of thing. Other questions? I should mention that the importance for numerical relativity. So clearly the way I've been phrasing it is a lot like the way you might phrase a numerical problem, where you want to set up some initial situation and then ask what happens as time evolves. So often this is how, or this is the starting point anyway for how you do numerical. Okay. I'm going to talk some more about the constraint equations. The dynamical equations I'm going to leave for later. But I want to talk about, I want to explain in what sense the constraint equations are Gauss' law for momentum. I'm going to do this in an example, which is spherically symmetric. Sigma with where I'll assume that the sigma that we're talking about has k be equals 0. So in the book of Poisson, this is called a moment of time symmetry. The reason for that is because this is like saying that h dot, the time variation of h on this surface, is 0. It could be that you're in a static spacetime. If you're in a static spacetime, you can always find a slicing when this is 0. Or it could just be that you're instantaneously static. Okay, so what are the constraints in this situation? What can this initial slice look like? Well, the spherical symmetry tells you that the metric on sigma can be written in the following form: dr squared 1 minus 2 m of r over r plus r squared omega squared. I've written it this way in order to make it look like the Schwarzschild solution, but we could have just put any old function. M here is this is not Schwarzschild. M is a function of r, so we could have put any old function here. And this is the most general spherically symmetric thing, right? Then the constraint equation for Ricci becomes r of h is equal to 4 m prime of r. Well, sorry, if you just calculate the Ricci scalar for this induced metric on the hypersurface, then that's what you get, 4 m prime of r over r squared. And then the constraint equation is that we set this equal to 16 pi rho of r. So that's this equation here. So we assumed that k was 0, and then we should set the induced curvature to 16 pi rho. We can solve this equation for m. So this is think of this as del dot E. So think of this as del dot E equals rho in electromagnetism. It's a differential equation for the field in terms of the charge distribution. We can solve this equation from M just as we would to get the integrated form of Gauss's law. So the integral form of this is M of R is equal to the integral from 0 to R, dr prime 4 pi r prime squared rho of r prime. Just like how Gauss's law would tell you that the E component of the field strength is some integral of r prime squared. That's the charge density. So this is showing you very explicitly that this is literally like Gauss's law, but for energy instead of for charge. Take the energy that you just integrate up the total energy density enclosed, and that gives you this M. This is also, by the way, probably really, they're not quite the first, but I guess this is a good demonstration of the fact that we were justified in calling the M in the Schwarzschild solution the mass, or the energy of the Schwarzschild solution. Because, as we see here, if you did have some spherically symmetric mass distribution, this really would be adding up all the energy that was on the inside. In the actual Schwarzschild solution, it's tricky because there's a singularity at r equals 0, and you can't exactly do what I just described here. I was talking about a smooth hypersurface. So this is more like for a star than for a black hole. Similarly, the other constraint equations tell you about the enclosed momentum, which in this case we've just assumed is 0 because we set the extrinsic curvature to 0.
In the case of Schwarzschild, why would TAD be 0 as well?
Sorry?
In the case of Schwarzschild, wouldn't TAD be 0 identical?
Well, I don't think it's 0 at the singularity. I think it's certainly 0 away from the singularity, but I think you should sort of think of it as if has some non-zero contribution from at the point 0.
So we'd still be justified in using that equation with something non-zero on the right-hand side?
It's just like Gauss's law, where you have to, like, if you have a delta function source at the origin, you can calculate it by calculating the fields far away. It's just like that. So this equation basically tells you that there must be some energy at the origin in the Schwarzschild spacetime. Okay, that's sort of all I'm going to say about the initial value problem for now. And I want to talk about something else. Other questions? We'll sort of come back to the initial value problem when we talk about the Hamiltonian. The Hamiltonian is what tells you, given some initial data, the Hamiltonian is what tells you how to go forward in time. Okay, so this is another application of what we've learned about hypersurfaces. Our goal now is to understand what are called thin shells or gluing solutions. So the goal is to construct nonlinear solutions, that is nonlinear analytic solutions of the Einstein equations by gluing known solutions across a hypersurface. Okay. So the idea is that you have some metric that you knew, call it G mu nu minus, then you stick in some wall, sigma. On the other side, you put in some other metric that you know, G mu nu plus. And we like to construct nonlinear solutions by somehow gluing these known solutions together. Now why would we, okay, so that's what we're going to do, but first let me tell you why we would want to do such a thing. There are basically, well, and the answer is basically that nonlinear gravity is really hard, and we just have very few analytic solutions to work with. We have the Schwarzschild solution, we have lots of linearized solutions like gravity waves, but in general, finding nonlinear solutions, especially in time-dependent situations, is just extraordinarily hard. And there are kind of two ways to do it. One is numerics, and the other is by using thin shells like this. There are a few exceptions, but most of the dynamical solutions, most of the nonlinear solutions of the Einstein equation that I know of, which are not stationary, so the ones with real dynamics, are some form of these gluing solutions that I'll describe. A couple in particular that are important are, okay, so I just said nonlinear dynamics. For example, we'll be able to talk about things like collapsing black holes in this situation. This is an idealized version of a collapsing black hole with a thin shell, but actually we'll also be able to construct more realistic non-thin solutions by gluing. The second application, big application that I can think of, I know we might talk about this one a little bit, is to brains. So in various exotic theories beyond the Standard Model, both string theories and slightly less exotic things like extra-dimensional scenarios for physics at the TeV scale and beyond, often branes are invoked. So branes are hypersurfaces, or well, of various codimensions. They're surfaces of various codimensions. But in particular, well, let me just give an example. The Randall-Sundrum model for understanding the hierarchy problem in the Standard Model, the starting point is to suppose that we live on a 4-dimensional hypersurface in a 5-dimensional